Okay, welcome back. So you've seen what the difference is between real numbers and imaginary. We're going to stick with real numbers for our solutions. You've seen what an inequality symbol is and the fact that it points to the smaller number. But now I'm going to introduce inequalities that have variables in them. And in those situations, those are inequalities that we want to solve. And when we solve them, it's not like an equation where there's one answer. Sometimes equations have two answers if it's a quadratic equation. In this situation, there will be many answers. In fact, there'll probably be an infinite number of answers that are correct. So let's talk about solving inequalities. And we'll start with single inequalities. So this is still section C.1. And we're going to focus on solving inequalities. Okay. Now, I know before we talked about just the inequality symbol in general, and it was pretty simple, right? The arrow points to the smaller number, and it's true. So all I can really say about that is true or false. And we hope it's true. That's what we want it to be. But the minute you put a variable in there, it says all real numbers, we'll say x, which are greater than 4. So let's look in this bubble here that is the solution set, and let's see what lives in there. So what's in the solution set today? 5, 6, 7, 100. What else is in there? Well, pi can't be in there because that's 3.14, but how about 2 pi? That's 6.28. Sure, that's in there. How about 123 over, let's say 3. That's in there. Okay. What's not in there? Well, pi isn't in there. It's out here. 0's not in there. It's out here. Square root of 2. That's not in there. So you get an idea. You get an idea of what's in the solution set and how many numbers reside in this solution set. There's an infinite number of numbers, right? But are we going to express it this way? I don't think that's a great way to do it. So we would express the solution a couple different ways. But before we do that, let's solve inequalities. Now, to solve an inequality, what I want you to do is I'd like the variable x on the left. So I don't want your solution to have the variable x on the right. We don't want it over here. The most logical explanation of your solution set is when the x is on the left side. Inequality symbol goes here, less than or greater than. And then generally, a number maybe goes over here. There's where your number goes. And that's it. It's solved. And this is a perfectly legitimate way to express your solution set. Because if you say x is less than 4, you're saying all numbers, all real numbers that are less than 4. Okay? So that's a valid expression of your solution set. But again, I need you to get the x on the left side. That's really important. Because I often see solutions where the x is on the other side. And while the inequality might be correct, you're not really expressing the solution set in a logical way that is most easily understood. I understand x is less than 4 means all numbers less than 4. Now, there is an equivalent version of this. It looks like this. This is equivalent. But I'd like to avoid this equivalent version if we could. It says right here that 4 is bigger than all the numbers in my solution set. And we know that's certainly true, because right here it says all the numbers that are smaller than 4. We're talking about numbers like 1, 2, and 3, and 3.9, and 3.999. Okay, don't forget those. Those are in there too. So this says 4 is bigger than any number in your collection. That is true. 4 is bigger than 3.999. 4 is bigger than 2. Now, if you end up with the x on the wrong side, what I'd like you to do is take this inequality, draw a box around it, imagine this is a clear piece of plastic, and take this clear piece of plastic off the board, off the paper, and rotate it. And if you do, you rotate it, the x will show up over here, the 4 will show up over here. I know it would appear backwards. But as you rotate that clear plexiglass piece, the inequality symbol will rotate. And you notice that the arrow is pointed at the x and the arrow is pointed at the x. So this is equivalent, and this is the more acceptable version of the solution to your inequality. Now, how do you solve a single inequality? Because sometimes your inequality will look like this. You solve an inequality the same way you solve an equation. Pretend that's an equation. In fact, this one is kind of an equation. There's an equal sign right there. Now, if this was an equation, you would move all the x's to one side, preferably the left side, like that. You would move all the numbers to the other side, like this. And then we would see what the result is. Now, this is 2x minus 4x is negative 2x. This is greater than, that does not change. And this is gone, and this is negative 12. So far, it looks like solving an equation. Now, if you were solving an equation, naturally you would say that the next step is to divide by the coefficient in front of the x. That is true. There's one rule you really need to remember when you're solving inequalities, and that is, during the solution process, if you multiply or divide by a negative number, you must flip the inequality symbol. I don't mean the presence of a negative number. You can have negative numbers. It's the action of you multiplying or dividing while you're solving. We're about to divide by a negative number. Let's do it. Divide both sides by minus 2. Divide both sides by minus 2. The minus 2's cancel, so the x sits on the left side like it should. Minus 12 over minus 2 is 6. And you must reverse the inequality symbol because we have divided by a negative number. Do you always reverse the inequality symbol? The answer to that is no. So sometimes people know about this flipping the inequality and almost do it every time. If I just divided by 2 on both sides, I would have left the inequality symbol alone. Now that's solving a single inequality. What about a double inequality? Let's talk about that. Then we'll talk about how to express your answers. So let's solve a double inequality. Okay, double inequality looks something like this. Two is less than x is less than 4. So here's what it's really saying. It says the solution set are all the numbers between 2 and 4, but not including 2 and not including 4. Now, I could include one of the endpoints, and why don't we do that? So now 4 is included. So what's sitting in the solution set? Well, 2 is not there, but 2.1 is there, and pi is in there, and 3 is in there, and 4 is in there, and 3.25 is in there, and 2.79 is in there. Let's see, square root of 5 is in there. So a lot of people look at these inequalities and think, oh, it's just 2, 3, and 4. But nope, there's always going to be an infinite collection of numbers in there because it's real numbers. It includes all the fractions, all the decimals, everything in between. So you have to know if the endpoint is included or not. Now, how do you solve a double inequality when it's not as straightforward as that one? So this inequality, double inequality, has x isolated in the middle, and I want you to solve a double inequality so that x is isolated in the middle. One more thing. I want both of these arrows to point to the left. So a couple forms of double inequalities that don't make any sense. That doesn't really make much sense. Neither does this. So in order to be a double inequality, the restrictions or the expression of a double inequality has to be something that both of the inequalities have to be true at the same time. How can you have a number that is both greater than or equal to 7 and, let's see, that would be greater than or equal to 1. So let's try this one. Less than, let's do this double inequality. Number that's larger than or equal to 7, but at the same time, 1 is bigger than my number, implying that x is smaller than 1. So how can a number be smaller than 1 and bigger than 7? It's impossible. So just make sure that your double inequalities always point to the left. So now let's solve a double inequality. So what if we had in the middle a 2x plus 3? Let's say they already pointed to the left. So that's actually going to make life a little easier. On this side, I'm going to put a 5. And on this side, I'm going to put a minus 11. How's that? Now, to solve that double inequality, your goal is to isolate x in the middle. And to isolate x in the middle, solve it like you would an equation in a sense. Let's get rid of the numbers first in the middle. So the first thing we'll get rid of is the 3 by subtracting 3. There we go. So now I have a minus 14. It's less than 2x. It's less than or equal to 2. Next thing, let's get rid of this coefficient 2 right here. So we'll divide by 2, divide by 2, divide by 2. And we end up with negative 7 is less than x is less than or equal to 1. This makes sense because the arrows point to the left. So it's all the numbers between minus 7 and 1. All the numbers between minus 7 and 1, but also including the 1. And I think this is a good opportunity to talk about the ways that you express your answer. There are really 3 ways that I'd like you to express your answer. One is using the inequality. The second is to use the number line and just highlight the number line with the numbers that are in your solution. And the third will be interval notation, and I'll talk about that briefly in a moment. Let's start with the inequality version, which is right here. We don't have to do much about that. All the numbers from minus 7 to 1, including 1. Arrows point to the left. The x is in the middle. Everyone's happy. The next thing we're going to look at is the number line. So if we put 0, let's say over here, we'll put 1 over here. Minus 7 would be way over here. And it's not really required that we go and label the rest of it in here, although we certainly could. Now, the minus 7 is not included in the solution set. And to represent that, I want you to use a soft edge, a parenthesis. The 1 is included. I want you to use a hard edge, which is a bracket. And then I want you to bold up everything in between. These are the numbers we're talking about, okay? Might be a good idea to mark these off. Minus 6, minus 5, minus 4, minus 3, minus 2, and minus 1. Therefore, we know that those are all in the solution set. So this is how to represent it on a number line. Okay, the next thing we're going to look at is what's called interval notation. And for interval notation, basically, we take the information from the number line, but we don't need to actually write the number line. So we take the parenthesis from over there, we take the bracket from over here, and the endpoints, minus 7 and 1. So interval notation is a really nice summary of your solution set without having to draw the number line. And you can see numbers that are included and numbers that are not included. So what do we do when things are open-ended? What do we do when infinity is involved? X is greater than 3, number line. Okay, all the numbers greater than 3, but not 3 itself, we need a nice little soft edge parenthesis there, and we bold up all the numbers to the right. In fact, isn't it interesting that the inequality symbol points to the right? and so does this arrow. That'll always be the case. So how do we use interval notation on this? Well, we're supposed to use the symbols from here and here, but there is no symbol over there. Well, we can start with, at least we can start with the 3 here in the parenthesis. Now, what number would be the last number in the sequence? 4, 5, 6, 7, 8, 9, 10. Well, infinity would be the last number. Now, in order for the number itself to be in your solution set, you have to be able to put that number right in your hand and say, hey, the number 3 is right here as included. Now, it's not included in this case, so that's why there's a soft edge. But look at the end number. It's infinity. So we have to be able to take the infinity and say, here it is, guys. Infinity is included. You can look at it. But who can get to infinity to grab onto it? Nobody can. So in that case, even though we think it's included, it's a soft edge to represent the fact that infinity is not included. Okay. Now, there are different kinds of intervals that we want to look at. And I want to discuss the different kinds of intervals. And here they are. There's really several kinds of intervals here to look at. But primarily, we're looking at bounded and unbounded, open and closed. So if you look up at the top, the first one is a bounded open interval. Bounded means there are boundaries. Bounded means that there is a start and a stop, in this case, A and B. It's open because the endpoints are not included. The next interval is a bounded closed interval. It's bounded because there's a beginning and end, A and B. It's closed because you can almost say the case is closed. The endpoints we know are included. Now, if one endpoint is included and the other is not, we say it's neither open nor closed. However, it is certainly bounded. Unbounded intervals are below, and unbounded intervals have no boundaries, basically, on one end or the other. And that's when infinity or negative infinity is involved. It's open if the other endpoint is not included. It's closed if the other endpoint is included. And, of course, the last case is minus infinity to infinity, which is the entire line. The real number line. So I think we're going to stop here, and we're going to continue with inequalities in the next lecture. And the next lecture will be about absolute value equations and inequalities, and we'll also include the quadratic inequalities in that one as well. So stay tuned for the next video. When you're ready for it, check it out. I know we're beginning slow, and some of this is pretty simple stuff, but I want to make sure everyone's on the same page here. So yes, it's, something to start slow with, but as we get into the more difficult concepts, you're certainly going to want to watch these videos, and as you can see, I'm going to explain everything in great detail. So stay tuned, and we'll see you in the next video.